For today, we're very pleased to have as our second invited speaker, Richard Socha, who's the Chief Scientist at Salesforce. Richard actually also has a lot more connection to this class because for several years, Richard was involved either as instructor or co-instructor in teaching this material at Stanford. So he sort of knows the course pretty well. And so today, he's going to be talking about some of the challenges and recent work in doing multitask learning in natural language processing. So welcome, Richard.
Thank you. Hello, everybody. I'm excited to be here. I want to talk to you today about what we in short call decaNLP. I want to first give a big shout out to Brian McCann. He's the first author of this paper, and I've pitched this idea to a lot of people in the last 3 to 4 years, and most people were like, this is too much pre-processing because you're trying to do 10 different tasks in one model. That's sort of where the decathlon wording comes in. But he really stuck to it, did all the pre-processing and all the things that you now know, like tokenization. It turns out a lot of different data sets have a different conception of what a word is. It wasn't 2 words or 1 word and things like that, and that changes how you write all your evaluation scripts and all of that. So Brian is a really phenomenal researcher with us in the group. Nitish has helped us a lot on the optimization side of this, and then Semmings, our director of research, has done a lot of really phenomenal work. It's kind of helpful in pretty much all our projects. So I'm going to tell you a couple of different lines of reasoning that led us to this idea of multitask learning. And the first one was sort of trying to take a step back and looking at the field. And I know it's not like that much of a historical class, but basically pre-2010, most natural language processing had kind of these very hand-designed features. And we basically just had machine learning kind of learn weights in the optimization procedure for these human-designed features. And so in 2010, Chris and I and others sort of started to work in deep learning for feature learning. So everything was a word vector. Now we can backpropagate into them and actually learn those representations. And I think currently we're kind of in a state where we do a lot of deep architecture engineering for specific tasks. And you've seen this already. You have like an NER model, you have a question answering model, you have a translation model, and we basically now, each of these communities has at least converged on is probably some kind of neural network, but there's still a lot of different kinds of architectures of these neural networks that you're working on for each different task. And so the question is like, okay, if we're going to probably do that for another couple of years because we're making good progress, but what's sort of next on the research side? And what I actually love about this class so much is that you go from like maybe not knowing much about NLP at all to you can basically understand the state-of-the-art research papers as they come out now. And this is one of those. So why not continue to work in this multitask regime? In some ways, I feel like the community is a little bit like this cute dog where we kind of randomly restart after every project. And it's kind of clear to me that if you have a lot of training data and you define a specific data set and task on that data set, you start to architecture engineer on your model to hill climb on a particular metric or leaderboard or publications or products or whatever it is. Then as long as your data set has roughly a good representative set of 1,000 times the number of output classes that you have, you'll probably get it into a regime where you're in the 80 to 90% accuracy, or F1, where you're basically doing pretty okay. And of course, when you look at, for instance, ImageNet, you have 1,000 different classes in computer vision, 1,000 different classes, each has 1,000 images. So if you have roughly 1 million images, you do pretty well. And in machine translation, ideally, I have many more. I have like hundreds of thousands of words, so you want many millions of examples of each of the words in their context. And of course, the caveat is machine translation doesn't work to the level of humans, but it works well enough to have it at least in products, and even the best human translators use it as sort of a pre-translation and then sort of clean it up. And so it's also clear to me that in this regime, and if we want to get to sort of more general AI features, we need to have some kind of more continuous learning of a single model. Because if we keep restarting at every project, we're never going to get to a single model that kind of encompasses more and more of the complexity of natural language. And when I say we start from random, you of course know that that's not quite true, because we do have some things that we pre-train, namely word vectors, and in computer vision we have even more things. And so in some ways that is an aspiring ideal for NLP, because in computer vision you would be kind of crazy to not use some kind of convolutional neural network that is has been pre-trained on some kind of task like ImageNet when you start with your project and try to classify objects or do object detection and a lot of other things. And in some ways that the whole community could get behind it very quickly, because I mean, you know, once it worked reasonably well, because there was sort of a single blocking task in computer vision. If you can't even tell apart a dog from a cat from a house, it doesn't really make sense to think of even larger vision projects. And in NLP, we've had a lot of success with word vectors. You know a lot of those now. It started with sort of just a small window-based approach with word2vec and glove. Then we had context vectors that were trained on machine translation, but basically instead of just having a single set of words, we actually pre-trained some of the LSTMs that came on top of those word vectors. And the way we trained that was also actually Brian McCann's paper on contextual vectors was with machine translation. And then Elmo kind of replaced machine translation with language modeling, which of course is even better because there's even more training data and it still tells you a lot and kind of captures in some ways a more complex version of the distributional sort of hypotheses that we had in simpler word vectors. And in BERT, not quite a language model, but also kind of trying to predict words in their context, but pre-training a lot more layers and a lot deeper networks. And so we see the success of pre-training a certain set of weights. And so the question is, why not try to pre-train the entire model? As in including your output, your softmax, your pointer mechanisms, and everything, and then just taking a completely pre-trained model and trying to do something. And that is kind of the goal that we have. And so we sort of asked ourselves, why hasn't this happened? Why are we, you know, the first to think about like trying to pre-train the entirety of the model, the encoders and decoders and outputs and everything? And I think part of it is that NLP requires a lot of different kinds of reasoning. You've seen many of them already. You have some logical reasoning, like 550 people in this room, 25 leave. Are there still people in the room? And you kind of logically can answer that question. You have lots of different kinds of linguistic and emotional reasoning, sentiment analysis. You know, this is a typical Nicolas Cage movie, and then you need to know that that's probably a negative review, unless you like Nicolas Cage movies. No judgment. You know, visual types of reasoning and so on. And so I think partly because of that complexity, in the beginning the field didn't really make much progress, and then kind of separated, and I think in some cases kind of artificially separated into all these separate tasks. Like you have named entity recognition, part of speech tagging, and semantic role labeling, and so on. And in some ways, and it sounds kind of snarky, but you know, it made a lot of sense at the time, and it allowed us to make a lot of progress in the community. But basically, we started chasing these benchmarks, and all these different communities kind of started going off in their own ways. And you even have some communities that say we do general question answering, and there's literally workshops on general question answering. And when I asked the organizers, can I ask your model what the sentiment is of this tweet? They're like, no, that's sentiment analysis. Go to that different workshop. It's down the hall. But I'm like, that's a question. Why can't you answer it in the general question answering workshop? And so a lot of people then say, well, if you want to work on more general stuff, it has to be an unsupervised kind of task. And the future will not be supervised. I don't think NLP will be completely unsupervised, and we won't solve it completely unsupervised, because in the end, language has a lot of supervision for people, and I think for systems also. And you won't, you know, if you have a child and it's in the jungle, it'll probably develop a pretty good visual cortex by itself, but it won't develop language by itself. And then also, like, I think if you just allow AIs to talk to one another, it makes very little sense for them to try to come up with as inefficient of a communication protocol as humans have with, you know, sequential processing of language, because algorithms and computers could, if there's no supervision of human language, they could just communicate in much more efficient ways with one another. So I think it's fairly clear we need a lot of supervision in NLP. And so basically all of this has led us to trying to think about a unified multitask model for a lot of different NLP tasks. By the way, if you have any questions, just raise your hand. We can make this very interactive. Basically, we want this unified model to decide how to transfer knowledge and not have it sort of be manually assigned. Like in most cases, when you design your project, you say, oh, well, I know that named entity recognition and part of speech tagging help each other. Because once you know something is a noun, then it's more likely that it's also a named entity. And in this case, we want to basically allow for this single unified model to know itself how to do domain adaptation and how to share the weights. And that will hopefully then lead to a lot of transfer learning and zero-shot learning capabilities. I also think that if we get to this sort of hard goal of having a single unified multitask model, then we'll be able to more easily adapt it to new tasks, and we'll be also able to deploy it in production more quickly. If nowadays you want to build a little squirrel detector and connect it to your sprinkler system, you can just download some off-the-shelf software and it will basically kind of work. That is not the case if you try to do a pretty complex language project where you want to translate into some completely new language, or analyze some website and then do something else afterwards. So you also, when you actually try to deploy and use these kinds of tools in companies, you'll realize that there are a lot of different kinds of groups. There's the search group and the chatbot team and the translation team and the social sentiment analysis team, and they all use different models and they all deploy different models, and they all have to build a lot of overhead into the core of or around that core of an AI model. So basically, lastly, it was sort of what we had with this dog. I think that once we have this unified model, it'll also be a first step to being able to then continually learn this and just have a single model that just gets better and better over time and starts to capture more and more of the complexity of language. All right, any questions around sort of the motivation, high level? All right, so then is sort of the question, how do we actually make that happen? And then I first sort of sat down and looked at like the general sort of formats of all the tasks that you may experience in this class and that NLP sort of has as a field in general. And I think they can broadly be classified in these three different categories. Sequence tagging, you already know, things like NER or aspect-specific sentiment, where in a specific context you want to classify if a word is positive or negative. And then text classification, just a single label for the entire piece of text, and then sequence to sequence. A lot of different problems fall into that. And I actually personally love these three particular tasks: machine translation, summarization, and question answering, because they are immediately useful. You don't have to explain to somebody, oh, but why do you need the semantic row labeler or parser? If you're a layman and you on the internet, you understand immediately why it's useful to do summarization, question answering, or translation. And an improvement in those tasks kind of immediately translates into better products and people being able to communicate better and more efficiently with language. So that kind of analysis led us to think about these, what I call 3 equivalent supertasks of NLP. And basically, they are language modeling, question answering, and dialogue systems. Language modeling, basically trying to predict the next word. You've already worked on that. And usually it's only used to rescore or basically pre-train these days. But really, if you ask a question and then you try to predict the next couple of words, then that is also language modeling. And if you're able to predict the next couple of words after a question, like what were the named entities in this sentence, and then you just generate, Dresden was a location, Richard was a person, and whatnot, then you can kind of cast almost all of these tasks into language modeling. Similarly, question answering, you can ask any kind of question: what is the translation, what's the summary, and so on. And then with dialogue, right now it's kind of tricky because there are no really good dialogue data sets out there. And a lot of times you want some interaction, you have to run user studies, and most of the existing NLP tasks would basically be pretty short one-step dialogues. Like, what are the named entity tags? You give them and that's it. So it's a little bit overkill. And because of that, we basically converged on question answering as our main formalism. And here is now an overview of the 10 different tasks that we have. And we cast all of them as question answering. These are literally the training, the format of the training data set, and eventually also the way we formulate the test set. And you'll see basically for every single task, you have a context as some kind of document. Could be a Wikipedia article, could be a tweet, could be a longer document, whatever. And you ask a question about it, and you want to generate an answer. And I'm curious if you can think of any task in NLP that couldn't be formulated in this kind of structure. So let's go over some of these. The first one is sort of the standard task that you're all familiar with now, the SQuAD, Stanford Question Answering Dataset, where the answer is essentially a phrase somewhere in the context. But then the second one is something that you would never see in most generalized question answering workshops, and that is having a context of the single sentence asking what is the translation from English into German. And the output is, again, a sequence of words, but in this case, and we color them differently here, this is blue because all these words are basically not in the context and not in the question, and we will just generate them with a standard softmax to basically answer this question. We can also ask what is the summary, and you can see that those two, in some ways, it's artificial to make them into a natural language question. You could just say translate or summarize, and this is just like one kind of task token in your network. But actually half of these tasks, it makes sense because the question also is different for every example. So this one here is natural language inference, NLI, which you've covered also, where we want to ask whether two sentences entail each other or contradict each other, or there's some neutral relationship between them. You've seen a lot of sentiment, and this here is kind of important. We actually ask, is this sentence positive or negative versus just what is the sentiment? And why that is important is that you see here in green, this answer here actually comes from a word in the question. And if we formulate it that way, we can eventually do zero-shot learning, where we ask a new question that was never asked before for a new set of labels, and magically, in some cases, it still actually works, and it will, we can ask questions like, is the story happy or sad? And it'll still give us an answer, even though we've never given a training data set of a bunch of happy and sad stories. So it's kind of zero-shot classification that you get to, in some cases, if you formulate your questions in a way that the answer is part as a word in the question. Then we have semantic row labeling here. So what has something experienced, kind of a random weird question. Then we have a zero-shot relation extraction, who is the illustrator of cycle of the werewolf. We also have some dialogue state tracking. What is the current state in a dialogue? And the context just keeps on growing with the dialogue. And then we also have WikiSQL translation task, but not translating into another natural language, but translating into a SQL database query. It's actually a super helpful task. There's a lot of data out there that is stored in databases. If you can access it without having to ask somebody who knows how to program SQL, it will make that data available to a lot more people so they can analyze it, like business analytics and so on. And then here, Winograd schemas and anaphora resolution. Some people call this kind of common sense reasoning, but it's kind of mostly just anaphora resolution, trying to understand in this context who is the word, like who had given help. Was it Susan or Joanne? And then based on this context, you kind of should be able to figure that out. And again here, the question is different for every single example. All right, yeah?
When you're testing it, like when you ask, is this sentence positive or negative, does it sometimes do a different task?
Great question. So the question is, when I ask, is this sentence positive or negative, will it sometimes eventually accidentally switch to a different one of the tasks? And we actually have a slide on that. And the answer is, it's surprisingly good at knowing how to go about doing the task and where to get the answer words from. And yeah, it'll make more sense in a couple of slides once we go over the model. Any other questions about the question answering formalisms? Yeah.
Are you able to formulate text generation in the question answer format as well? Like, tell me a story.
Good question. So can we do text generation, like tell me a story from a random kind of, or in this kind of formalism? We don't have that as a task because largely it's really hard to evaluate. It'll tell you some random stuff and then is that a good story or not? Is it grammatical? You have to come up with a lot of evaluation metrics, which we actually are doing for some of the dialogue systems. And in the case of dialogue, why are they equivalent? Because the context can just keep on growing, and every time the user said something, you basically try to then predict the next answer in that dialogue. And so I think you could very easily use this to generate text. You basically just tell them like what's a good ending of the story, and you maybe start the context with like 2 or 3 words, and then you ask the model to generate more and more words in the formalism that we'll describe in a second. Yeah.
I was wondering, like, when you're training it and you're trying to teach it like a new task, does it like learn with less data?
That is an amazingly thoughtful question, and it's so important. We'll have a bunch of slides on it. So maybe we'll continue and we'll get to that question in a lot of detail, because that's sort of why we're doing it. And the short answer is yes, but we'll get to more details. All right, so these are basically the 10 tasks. And again, this is the actual format for it. So if you have a problem and you can cast it in this format, you can just take the open source code and run it, and it'll work. And so when you kind of analyze and think about what we've done here, in some ways we've taken the task that usually is kind of in your head, but it's not given to the model. The model is just given an input X and an output Y in almost all of these supervised systems. And instead, we're actually including the task in the inputs, in the set of inputs to the model. So you can kind of call this meta-supervised learning. So again, the question is kind of our task definition for each of these different tasks. The model has to figure out itself when to ask the question. That way it can also figure out itself when to transfer knowledge from these other tasks. And Y is again just the answer. So in some ways it's meta-supervised learning, and I'm quite excited because once you allow the task to be given to the model as input, it can kind of decide itself how to go about solving that particular task, and now you can learn a lot more powerful models. So once we had the data set, we thought, okay, how do we now solve this problem? The simplest way is you could just say, well, I have a big if statement, I have a classifier in the beginning, and I classify if this is a machine translation task, then run my machine translation model. And in general, in Python, that would still be just like one big Python model with a bunch of if statements, right? And that's not the goal, because then we wouldn't get to any of the transfer learning and zero-shot capabilities that we're hoping for. So we want to have the model, wanted to have the capability to internally adjust to these different tasks and make these decisions itself. And basically, all of those considerations and all of those thoughts led us to this model. So before I go into a little bit more details, I'll just like sort of give you the high-level overview. Again, you start with the context. You ask a question about that context document, and then we're going to generate the answer one word at a time by either pointing to the context, and you've had pointers already, right? Pointer networks, all that, great. Pointing to a question word, or choosing a word from an external vocabulary with your standard softmax classifier. And we'll have a pointer switch mechanism that will kind of choose how much to weight each of these 3 generation mechanisms. So let's dig a little bit into this model. Fortunately, in some ways, it's kind of just taking the best of the current sort of state-of-the-art techniques and putting them together in a way that generalize well enough. You can look at all the code on decaNLP.com. It has like thousands of stars and forks and stuff combined, and you can basically run everything in this on these experiments with just one command. It'll wget all the data sets and everything and run everything. You can really explore what it looks like, but let's dive a little bit into the details of what this model does. In some ways, again, it just kind of takes all the best ingredients from deep learning for NLP, most of which you've already learned about, and puts them together in a reasonable way. So we start with fixed clove embeddings. Eventually, we updated the embeddings to cove embeddings, and probably it'll work even better if you update them to bird embeddings. But at some point, we kind of have to move on and do other things. But basically, you have a fixed set of word vectors, and that is kind of important because in some of these data sets, they're much smaller than others. And as you know from Squad, if you actually backpropagate into the word vectors, you just do really, really well on your training data set, but then you won't generalize because most of the test documents will include words you've never seen before. So if you change all the word vectors during training, it won't work very well at test time and won't generalize to unseen words. So fixed clove embeddings, if you don't have word vectors for unseen words, we also have character engram embeddings. Then we pipe them through a simple linear layer. And then we have a shared bidirectional LSTM. with skip connections. And so it's a deep one, so you skip to higher layers, and it's shared between the context and the question. So they have basically the same set of weights. Then we have a co-attention layer, where we basically just have outer products between all the hidden states of those two sequences. And again, have skip connections to circumvent those as well. So now you have kind of context or question-dependent contextual representations or representations of that context. Then we feed those into transformer layers. And we actually tried to use transformers for all the things. We're having no LSTMs or any of that. Unfortunately, the transformer layers were still very finicky and very hard to optimize, and there's a lot of trickery with the learning rates, and we could just not get them to perform really well on these 10 different tasks. Sometimes you had one transformer layer, one transformer network, and it worked really well on one task, but the only other transformer network that worked well on the second task had like half the layers. And once you tried to have one network with the same number of layers, it just wouldn't work on either of the two tasks anymore. And so yeah, unfortunately, as nice as they are, because they're nicely parallelizable on GPUs, they weren't yet robust enough to be used for this. So we have to have these LSTMs before and after the transformer layers. And then we essentially just have a standard sort of autoregressive decoder. We're given the last state, we generate the next word. And then we have these three pointer mechanisms. They're very similar to the pointer mechanisms you already know, but now on top of these very contextualized representations at the end of this encoder. And it basically learns to either point to question words, context words based on the hidden states, or have also a standard softmax. And then we just basically have a weighted sum, convex sum of these three different distributions of output words. All right, so I think these are mostly standard components that you've already have already seen in all their details, but do you have any questions about how we put them together? Okay.
So if the output has to be a word.
That's right, the output has to be a word, and it's always either a word from the context, a word from the question, or a word from the softmax.
And the data pre-processing is different for each task.
So the data pre-processing is different for each task, but we basically had to normalize everything to have the same tokenization and all of that.
So do the double errors in the encoding just represent the bidirectional?
That's right.
Okay.
Yeah, but the double errors here are just bidirectional, so left to right and right to left for the LSTMs. All right, so what data sets are we using? I mentioned that that was a big headache in the beginning. We definitely wanted to include a lot of the sequence-to-sequence tasks that we felt like are very sort of high level and immediately useful. And in some ways, what this also shows you is that nowadays, you don't have to work as much on some of the intermediate representations in NLP anymore. You can just directly go for the end tasks that real users might care about, and then have these end-to-end trainable systems that really do quite well. And I've myself worked a lot on parsing, so I don't want to say we don't need it. There's certainly still tasks that you do need it for, but it's kind of surprising that you can just go directly to translation or summarization without having intermediate representations that were sort of very specifically hand-designed. So we had those three really interesting and hard tasks: question answering, machine translation, summarization. They actually also have the three biggest data sets of all of these. Then we had NLI, and basically all of these 10 data sets were publicly available. And in several cases, especially for translation, you could actually find much larger translation data sets, but we also tried to keep it to a size where normal people that don't work in gigantic companies with huge GPU infrastructures could still run experiments themselves. So universities and folks can still run it on basically, if you have just a single GPU, it'll probably take about a week or so to run an experiment. If you have multiple GPUs on one large AWS machine, you can kind of run an experiment in a day or two. And so especially for translation, right, you could get a lot more data than IWSLT. And each of these communities and data sets and tasks has their own metric. We actually tried to, in the beginning, we've had a lot of discussion about how we should define the measure of success for this project. Does it make sense to have a normalized F1 score for basically all the different tasks? But then we basically realized that these different communities have different metrics for a reason. And fortunately, at least, all of these metrics are from 0 to 100 in theory. Of course, in practice, you rarely ever see a translation system with 100 or even high 90s of a blue score or these really, really high RU scores. But in theory, they go from 0 to 100. And so we kept basically intact the different evaluation metrics for each of these communities, and we just said we're going to sum them up. And when we first talked about this, we had a lot of discussion with others also of like, oh, but translation is so much more important because it's much bigger and it's much more useful task than these silly like pronoun resolution Winograd schemas, which only have a couple hundred training examples. And so you should have weighted translation more. And then literally 5 questions later, somebody's like, why didn't you weight pronoun resolution more? That is a really hard task that captures sort of common sense reasoning and the complexity of language and semantics, and unlike all this like statistical pattern matching that you do in translation. And I was like, you should talk to that guy, and like hopefully in the end we'll just all agree that like it's reasonable to sum them up. And of course, you also have to tackle, when you run experiments in this, a lot of the complexity that you have in machine learning and stuff that very few people talk about, like having very skewed distributions. So you have translation, which has millions or hundreds of thousands of examples, and you have Winograd schemas that only have a couple hundred. How do you train that such that you don't just completely ignore the smaller data set? So we'll get to some of the optimization trickery that Nitish spent several months on in a bit, but I first want to sort of give you the first set of experiments. So as you can see from all the numbers, there's a lot of experiments that we ran to even get to this. And so we'll walk through this quite carefully. I think hopefully you'll get some ideas also for ablations or experiments that you might want to run in your experiments and in your final projects. So what are we looking at here? So basically on the left side we have single task performance. So here each number comes from its different model that was trained separately on just one task. Each column here is the same architecture. And on the right side here, we basically have, for each column is basically the same architecture and the same exact model. So here we have 4 different models, and here we have 40 different models. And each column, again, is the same architecture. And so the simplest first column here is just a standard sequence-to-sequence model with very few bells and whistles, and some pointers, but nothing sort of major. It's pretty deep, stacked, bidirectional LSTM, skip connections, all the standard, good, well-tuned stuff for sequence-to-sequence models. And then we added self-attention, this sort of basically transformer layers. Then we have this co-attention layer of the outer products that we mentioned in the beginning. And then we also added the question pointer, so having the ability to point to a word in the question. All right. Any questions about this table? We'll dig into some of the details. Okay, we'll dig into the details first, and then maybe you can think of some questions. So let's analyze what's going on in this table, because there are a lot of numbers, and you really want to carefully analyze and sort of distinguish. I think my first observation was, wow, we can have a single architecture. Like even this is not quite what we want, right? We want a single model, but even this kind of showed us, wow, you can have a single architecture that actually does really well. And somewhat randomly, in some cases, it actually had gotten state-of-the-art results. So WikiSQL, for instance, this architecture had the best model to translate natural language English questions into SQL queries, which was a surprise to us because it is the 9th data set. It was really not like a priority for us. And when we designed the model and thought about how to generate words and pointer mechanisms and so on, we just kind of had the standard context of SQL words, and we asked the question, what's the translation to SQL? And then somewhat surprisingly to us, this particular architecture had the state-of-the-art on SQL generation, and a bunch of folks in that community kind of picked it up more quickly. because it had state-of-the-art. And that's, unfortunately, it doesn't have that many other state-of-the-art numbers, which is why it's harder. It's actually a much harder task. And what you also observe is that in several of the cases, using the multitask model, so having a single model for all the 10 tasks, actually hurts performance at first. And this is also something you rarely read in papers, because papers have a strong selection bias to only publish positive results. And when you look at most transfer learning and multitask learning papers, there's sort of an outside of the actual model consideration of like, well, let's only combine tasks that we know will work well with one another, and if they don't work and hurt performance, then we just exclude them from our experiments. And so you don't see many negative task results in the literature. And there are a few papers here and there that study basically the opposite side of transfer learning, and that is catastrophic interference and catastrophic forgetting. So interference is when you train two different tasks in the same model and they interfere with one another and actually hurt each other's performance. And catastrophic forgetting is if you train continually, you first train on one task, then you train on a second task. People used to think, oh, well, basically the first task will be completely forgotten and you just work well on the second task if you train a neural network sort of in a sequential way, one task and then another. And somewhat surprisingly, we found that things aren't actually catastrophically being forgotten in these models. Turns out that if you train them sequentially and you add a little bit of the original to the first task, it comes back very, very quickly. So while the performance is really bad, you can get to the really good performance very, very quickly in very few iterations. So, but that's one of the many interesting sort of tidbits that we found in the course of this that we haven't even published yet. All right, so focusing on the transformer layers here, we basically find transformers do help the original sequence-to-sequence model a lot. So if you tune them carefully and you combine them with some bidirectional LSTMs and so on, they were very helpful and improved across a bunch of different data sets, in some cases quite significantly. Another observation is question answering and semantic role labeling actually can predict each other's performance quite well. If one works well, the other works well. And vice versa. If they don't work well, both of them don't work very well. And it's also interesting because both of those tasks have different questions for every training example. Pointing, so the question pointing is super important. We actually have, in some cases, twice the performance, even for, and this is kind of surprising to us, a simple classification task where you could just have a standard softmax, but instead of saying you have a softmax of entailment, contradiction, and so on, you just basically point to the word entailment in the question. And that was also the case for Winograd schemas that also benefited a lot from this pointer mechanism. Sure. Can we explain that? Why does it help so much? In some ways, I think partly is the whole architecture has gotten better and better at pointing. And part of the reason we actually do very, very poorly in translation, which is the only task that hurt in our first experiments a lot in the multitask setting, is that is the only task that now has to generate results from a completely separate softmax, whereas the rest of the architecture got really, really good at pointing to things to answer questions, any kind of question. And so, but in some ways, I think that is one explanation, but I don't think it's all of it. I think we still need to figure out more why this happens. All right, now multitask learning is the most helpful when it comes to zero-shot, and I'm actually very excited about that. So this is a zero-shot relation extraction where you have different kinds of relations that you might want to extract, and you might have never seen like the student-teacher relationship that you're trying to identify in a certain context, or a product-company relationship or something like that. And so that one actually benefited a lot and almost got twice as high in terms of the accuracy when you learned it with everything else. So these were questions it's never seen before, relations that it's never seen before, and it got twice as good and benefited a lot, especially from having seen other kinds of questions. And in some ways, we have to give a lot of credit to Squad too, because Squad as a data set kind of pushed people into thinking about pointers as a mechanism to generate answers. And pointers, we kind of see them like as a given, and they don't get that much credit, but they allow you to predict answers that you've never seen before at training time, to generate words you've never seen before at training time, which is actually quite amazing. All right, now the main observation though here is that you still, if you had an oracle that would tell you exactly which task you're currently in, and you would be perfectly kind of separating these into 10 different models, maybe they're all the same architecture, but there's still 10 different models, then you would actually still do slightly better than the first version of this multitask learning model. And that is largely because we chose to include a bunch of different tasks that have nothing to do with one another, and we wanted the community to start thinking about tackling catastrophic interference. Right? If you learn like a new language, or you learn how to understand social media on Twitter, you don't replace all your language and your brain. You have one brain, it keeps getting smarter, you keep learning new skills, even when the skills that are new to you are very, very different from old skills. So in some ways, we may have made our lives too hard. And now we're actually thinking, okay, maybe if we want to publish a nicer paper on multitask learning, we just look at all the tasks that do help each other. And then we just have groups of tasks. And then you can very quickly publish some nice state-of-the-art papers. But basically here, we're still quite significantly away in the DECA score between 10 different models and a single model. Now, this of course is kind of an oracle score. That's why we put it in parentheses, because you don't actually have this oracle. And in some cases, it's quite easy to build an almost perfect classifier. So, separating what is the summary based on that question and what is the translation from English to German, you can do with almost 100% accuracy. But squad question answering and zero-shot relation extraction and question answering as a semantic role labeling, those are actually easily confused in terms of how to generate the answers, and you wouldn't quite know into which model to route this. So in some sense, this is kind of theoretical. All right, now I mentioned that we have this complexity in the optimization strategy, and this is one of the many sort of problems that don't get that much coverage. But when you have a very imbalanced or skewed data set, it's easy to lose track and basically overpower the smaller data set tasks. And so the first simplest training, we actually tried a ton of different training strategies, but in the end, this fully joint one worked quite well. But I actually promised to wait for questions on this table. So any questions on all these results so far? Yeah.
So since you mentioned that if you had an oracle that could tell you which task it is, you could do better with having 10 different models. So did you try training a model on determining what task is being interested in this particular question?
We did, and so it confused squad and those two. Basically the other two types of problems that were also cast as question answering. So it confused those. But then a lot of the others, it was able to very perfectly do it. But then you basically, as soon as you were to try to then build the whole model and get a DECA score, if your classifier is even 90% accurate, you basically multiply this by 0.9 and you get things so hard that it's not competitive anymore. So it is actually hard if you try to just build that whole system and keep adding sort of if-then-else statements to make that into sort of a single system. Yeah.
Have you tried telling the model what kind of task it's doing, just giving it an indicator of the kind of task that it is doing?
I mean, in some ways we did in this case because we only trained each model separately on it. Only through the question.
Yeah, because I was thinking maybe it's not that important that the model figures out what we wanted to do in a practical application, because we could just tell it what we wanted to do right now.
In some cases you could tell. So the question is sort of, even in the multitask setting, you could have an extra kind of token to say, now you're doing summarization, so and that's another input. In some ways, whether you have a summarization token or you ask what is the summary, it actually, I don't think, makes that big of a difference. It's just now you can query this model in very natural language rather than having to know kind of a special token to query the model. And we'll see actually in a couple of slides that the model is not confused when it comes to how to generate the answers. So for every of the tasks, it knows very clearly how to generate the words to get to a reasonably accurate answer.
Just to clarify, for the single task performance, did the model see all of the data and then you just picked the one that happened to be best on that task, or did it only see the subset of data?
Oh, great question. So how do we train these single task models? They're only trained on that data set. So the squad number here is just a single model that has only seen squad training.
So your point about the pointers to the question for the classification, you're saying that you think that's just a generally more helpful way to do classification than
somewhat surprisingly, even in the case here where we had, where it says multi-NLI, this particular model, I mean, if you just have the standard sequence to sequence, it just generates, also with a softmax that label. So in that sense, it's quite similar. But yeah, it was actually better able to just point, which actually led us for a while into thinking about maybe we should have a project where we just say point to all the things and just get rid of softmax classifiers forever. The problem is when you then try to do translation also, it's like, okay, what do you point to? And then you kind of pre-train it, you do some alignment, and it gets kind of very large, and you point to a lot of different, like you may have like tens of thousands of potential candidates. So we kind of discarded it as like a single unifying model for all the things, but you could point to a lot of different, like a lot of these tasks you could actually point to, and I think it's another interesting side project that could spawn from this, yeah.
Just as a quick question, how sensitive, or did you test how sensitive the individual performances across tasks was when you slightly perturbed the relative weights of them in the loss function? So
the question is how sensitive were the tasks if we were to add weights to the different tasks. We did in the optimization, kind of did a lot of trickery on how to train it, but we never said this task only matters like 0.5 or something, so we didn't do that analysis. Yeah?
So co-attention seems to be hurting it a bit.
In some cases, yeah.
Is it a bit of evaluate on self-attention and keep it pointer, but no co-attention? Or is that kind of like, oh, we already saw the test data, so like we can't do this again?
I mean, these are all dev sets, but you could definitely do even more architecture engineering. In fact, there's this whole field, which I don't think you've gotten to, right? Neural architecture search. Yeah. So like you can actually combine your reinforcement learning and you say the action space for the reinforcement learning agent are trying to have a couple of different modules of neural nets. Like maybe you want to have like a CNN layer and then like a memory layer and then an LSTM layer and then maybe it's bidirectional, and you basically let a reinforcement learning agent figure out all of these decisions. So I think it would be phenomenal to try to apply neural architecture search not to what's usually being done, which is we already know how to do image classification, we just do it slightly better with NAS, neural architecture search, but we actually try to find a single architecture for multitask learning, which we don't know. The problem, of course, is that already getting to all these numbers took a lot of compute time and a lot of fiddling around with stuff. And it is, I can only give you sort of an idea of like how often we would say, oh man, we got like this really amazing result on this task, but it needed this learning rate. And it turns out the same model, same set of hyperparameters, everything, but this other task to get to good performance needed a much higher learning rate. And now you try to combine those two tasks only together, and you're like, okay, how do you choose your learning rate now? You choose the, if you choose the task, the learning rate from the task that is, bigger, then the smaller task just doesn't work well at all because it needed this higher learning rate. If you use the higher learning rate that the smaller task and smaller data set did really well on, then the large one just overfits and doesn't work well either. If you try to do the average, neither of the two work. Like there's a lot of complexity in trying to do multitask learning. That's why it's such an interesting, I think, research challenge. Any more question about these first set of results? They will get better. We have had some ideas already on how to improve them. All right. So how did we actually train this whole thing? We had tried a lot of different things, but in the end, this very simple, fully joined training strategy actually worked the best. And that is, you basically take a mini batch from each of the different tasks, and you just train on that mini batch from that task. So basically just going through all the 10 tasks and then round robin go through them. Now, it turns out that does not work quite as well as another training strategy. And if you look into optimization strategies in neural nets, there are actually a couple of papers on so-called curriculum learning, where the idea is you start with training your model with simple instances of your problem. So in translation, for instance, you start training with very short sentences, and then you go to larger and larger sentences, or longer and longer sentences. Now, it turns out for multitask learning, you actually want to do the opposite. You want to do anti-curriculum learning. And that is, you start with the hardest tasks and you iterate on those for a while, and then you add the simple tasks later on. And to some degree, I think this is intuitive, because when you train this very gigantic and powerful model on a very simple task, like sentiment, and you just need to classify everything to be positive or negative, you train all of these weights and you arrive in sort of local optima that are quite deep and very specific to just generating these two words. And if you then try to get out of this local optimum for that very simple task, and then try to generate all these other kinds of words and point to different, words it's never seen before in squad, it's very, very hard to come out of that local optimum. And that is sort of my intuition of why it actually makes more sense to say, let's start with squad and machine translation and a couple of these harder tasks, make the model very general purpose, has to generate a lot of different things, create a softmax, German words, it has to point to all kinds of different words and be able to parse all kinds of different Wikipedia paragraphs. And you do that a couple of times. And then once you've finished this sort of pre-training stage or anti-curriculum, then you move on and add sort of the simpler, smaller tasks. So with that relatively simple change that did take us a lot of different experiments to get to, we actually closed or went closer to closing that gap, and now we're only sort of 14 away, right? Yeah, 14 or so. But there's still a big gap, and the biggest nuisance and issue that we had was with translation. Basically, if you look at all of these, most things are kind of similar, get slightly better, and it's sort of a toss-up, but then and roughly similar. But translation was really bad. It's almost only half the performance in the multitask learning setup. And part of that is because translation was the only task that had a very large softmax vocabulary of words that were in no other task. And most of the other tasks actually were doing really well with pointing. And so my interpretation of this was that the intermediate layers, all these representations that we learned with bidirectional LSTMs and transformers, they got really, really good at being pointed to, like creating hidden representations that the answer module can point to very accurately. And then you have this one task that is like, I don't point to almost anything. I basically just generate other words in a different vocabulary. And so those hidden representations became less useful for that task. And so that was one of the insights, and led to one of the ways of trying to improve this. Now, one of the interesting issues that we had is when we improved the model, the single model for all 10 tasks, a lot of times we said, well, but now we also have to go back and run 10 more experiments on all the single tasks to have a proper comparison, right? Because if you tune the thing you care about and you stop tuning the thing you want to show you can do better then that's not fair. So you always want to give as much TLC and focus and experiment time to your baselines. And so in some cases, we actually improved something, but then we improved both the 10 separate models and our model. In some cases, like the 10 separate models improved even more, so the gap got even larger, which is kind of the opposite of what we wanted to show, but in general, it's better for multitask, for the architecture overall. So basically, we started with this fully joined training, and we have this sort of set of single models that we could, in theory, with some oracle, kind of just sum up in their scores to get a Deca score. So the gap started at 23. And then we basically did this anti-curriculum training, which lowered the gap to 15. So we're kind of excited, making good progress. Then we switched from GLOVE and used COVE, so contextual vectors, which actually increased the gap a lot again. So everything got better, but the 10 separate models got even better than the one single model that does the 10 tasks. So the gap got bigger, but everybody's performance increased. So it was still overall a good thing. And then we basically figured, especially with this machine translation issue, we shouldn't just pre-train on Squad, but we also should include machine translation in this pre-training in the beginning, so the model doesn't just start learning to point. And that helped us to reduce the gap between the 10 separate models, Oracle, and the single model to about 5 points. And then we basically said, okay, translation is still not that good, we just keep oversampling. So every time we go through one of these round robin mini batch sets, we just always include machine translation. And that basically allowed us to then reduce the gap to just a single point. So now we started several months ago at 586, and now the single Oracle with 10 different models, if you were to sum them up, gets 618. And the better contextual vectors and tuning and adding a lot more translation. And translation is still not as good as we would like it to be, but now several of the other tasks benefited a bunch, and now we're basically 1 deca score away from having a single model that does as well as 10 different ones. And you can basically, you could run even more experiments. In some ways, you could burn millions of dollars on AWS cost here, because most of the time we kept the hyperparameters of these different models the same. Like each of these, you could also say, well, maybe this multitask model needs to have 50 more layers, or maybe 19 more layers, or maybe 5 more layers, and maybe they should be 1,000, wider in their hidden dimensions. And you could basically run a lot more experiments. Maybe, hopefully, eventually the community jointly does that, and then we can kind of move towards that. But we figured, okay, we're pretty close, so we moved on to some other things, which maybe I'll tell you about next year. But basically, let's do some analysis of what happened in this project. And this is kind of, I think, something that I would encourage you all to do as well. Like you can chase the numbers for a while, and in some ways, you should always be skeptical about your evaluations. And in some cases, you've seen, or we've seen in the NLP community, people like basically just optimize blue scores for translation for years. And then somebody came out with a paper and said, well, it turns out blue metrics and human evaluations on how good of a translation is this aren't actually that correlated. And you're like, oh, that sucks. We just spent years of our lives tuning that metric and publishing a bunch of papers. And so in some ways, all of these metrics have flaws. Roux score summarization is a super subjective kind of task. And in summarization, for instance, when you analyze the errors, you often realize that word vectors have problems too. So for instance, a word vector for Jason, John, and Jeremy are all kind of the same, right? They all have similar distributions, similar contexts, windows, and so on. And so word vectors of names are very similar. And so in summarization errors, you realize, oh, well, this news article talked about Jeremy being kidnapped, but the summary said Jason was kidnapped. And you're like, well, in the evaluation metric, that's just one word is off, and like all the rest is correct. But it's a pretty important word. And so word vectors have like issues for summarization that are pretty fundamental, and I don't think anybody's tackling really well right now. So all of these metrics have issues. I would argue, though, that combining the 10 actually makes it less problematic and more meaningful than looking at each one separately. Because now you can't use the idiosyncrasies of one particular evaluation metric to just get like your score a little bit higher. Because then if you just tune with that particular thing in mind, it will hurt some of the other tasks, and you won't get to this sort of general NLP model that much more easily. All right, so now let's do some analysis of this model and look at, and this is the kind of thing comes to one of the questions that was asked, is the model able to kind of generate the right words for the right task? And here we basically looked at the distributions of how often the model generated words in these with these 3 different mechanisms, softmax vocabulary, context pointers, or question pointers. And as you can see, in the majority of cases, it knows exactly how to generate. So for question answering semantic role labeling and Squad and WikiSQL and summarization, it basically uses the context pointer. So it just points into the context document. And we know for Squad that is basically how the data set was generated, so that's the only thing that really makes a lot of sense. What's kind of cool is that in some cases, like summarization, it sometimes creates new words or that weren't in the context document, weren't pointed to. And for zero-shot relation extraction, it also sometimes uses this external vocabulary and in some cases the context pointer. So for the most part, this model is not confused how to execute on a task given this question formalism rather than the format of sort of this is the task, just do this particular task. Now, you might argue, okay, I'm not that impressed by having the performance be slightly the same with one model versus 10 separate models, even though it's nice if you want to deploy it, right? It's like uses less RAM and all of that, assuming they're the same size, or 1/10 the size. But what I'm excited about is more like the next couple of results, and namely sort of this transfer learning, domain adaptation, and zero-shot, these kinds of capabilities. So here we chose 2 data sets that weren't included in the original 10. And we basically trained a pre-trained model on this versus a random model. And randomly here, again, they're the same architecture. And pre-trained means the entirety of the model was pre-trained. All the encoders, including the decoder and the softmax and everything. And the 2 other tasks were another IWSLT language pair, namely translating from English to Czech, and named entity recognition, tasks you all know very well. So basically what we found is that it converges much more quickly in the beginning, and then there's still a significant but not gigantic gap. So this pre-training on these completely separate kinds of tasks had helped. And I think that's pretty exciting, especially sort of the quicker convergence, like learning more quickly whatever new task you come up with, which also means in some cases you can get away with less training data on these new tasks. Now, domain adaptation is kind of the simpler form of transfer learning, where you basically just have a different type of distribution for your words. We mentioned we have the Stanford sentiment tree bank for sentiment analysis, and then we analyze this on different sentiment data sets, namely Amazon product reviews and Yelp restaurant reviews. And out of the box, without any training, the model just got 80% accuracy on both of those data sets. And I think for practitioners, that is pretty exciting because you basically didn't have to train anything. It just kind of worked out of the box, download it from GitHub and run it. SNLI was slightly different. It didn't quite work as well. It's another natural language inference data set, but has very different distribution, different kinds of domains that these entailment questions are asked over. And here, out of the box, it achieves 62. But then once you fine-tuned it, and similar to these experiments here, continue to actually train on this data set, it quickly converged to 87, which was still 2% gain over a randomly initialized MQAN model. Yeah?
For the Czech experiment, did you evaluate how much less data you could get away with to achieve a given accuracy?
Did we evaluate how much less data we can get away with? We didn't, and in some ways, whenever you would run this experiment, you'd basically be like, you'd still not do as well. Like everything, all these models will still do better with more training data. So you just kind of, it would be a fuzzy kind of say like, fuzzy sort of result, right? Where you say, well, with 1/10, we might get to 50 and the other model might get only to 40 blues or something like that. But yeah, I don't have those numbers. Would be kind of actually also neat analysis to do. Yeah. Yeah.
So if you wanted to like train it on a new task, do you guys have some code on your like decaNLP website to like do that?
So do we have the code to train a new task? Yes, we do. You can just add it, make it into this format. Here's a context, here's a question, simple like CSV type format, and then you add it, and you can both like train the pre-trained model yourself. You can download a pre-trained model and just add it. It's all on GitHub. Yeah.
Do you know how this compares to using other kinds of pre-trained representations, like say BERT?
So it's a great question. So how does this compare to other pre-trained representations like BERT? So in some ways, people say BERT is kind of this model that does everything, but when you actually read the paper, you realize, well, it's a separate model for these different tasks, right? If you want to have a classification task, you have a little token in the beginning and you have a different top layer. If you want to do a sequence labeling task, you have a different top layer. If you want to do a sequence extraction task, you have a different top layer. So BERT isn't actually a single model for all of these different tasks. And then on all the results, there's a lot of extra tuning for each of the data sets and tasks that, different learning rate for this task, different size, there are different sets of BERT, and so on. So we're also super excited. We're like, maybe this is it. We'll just run everything on BERT. And then we looked into all the details, and there's so much excitement in the beginning. And then the more we dug through the details, the less excited we became as this being like sort of the answer, because it is not a single model. In some ways, it's probably better for pre-training. So instead of Cove, you can have kind of BERT at the very beginning. And my hunch is everything will get slightly better, but you still need to have a lot of the other sort of modeling architecture on top of it. And then the sad thing is, to really get the state-of-the-art results, there's a lot of very task-specific tuning with those last top layers. So if you try to unify that task-specific tuning, you lose a lot of the good performance of BERT. So unfortunately, it's not quite the sort of, just use BERT for it and you'll just have state-of-the-art numbers on all the things. I could probably go talk about it a lot more, but I think it still makes sense to think about some of the ideas from BERT, like basically add as one of the tasks language modeling. That would be very likely the task that helps the most for all the other tasks, and we should include that. It also would be nice to have a faster model. Right now, it's hard to do language modeling. It's very, very large. It benefits even more from billions and billions of words. It's hard to train the MQAN model, this current question answering model, with the co-attention mechanism of the question with an increasingly large context. So you'd have to kind of split it also. Like BERT works also reasonably well only for at most I think 500 words or so. And if you wanted to do summarization, you'd basically have to cut the original document to only 500 words and then try to summarize it. So there are a lot of devil in the details that they didn't have to figure out, because they said, well, we'll just sort of, just like word vectors, we can take them in, and then we do a lot of other stuff that is task specific with those word vectors or with the BERT architecture. I don't want to diss BERT. It's obviously amazing, and we are looking into trying to use ideas from it, but unfortunately it wasn't just sort of a silver bullet to solve multitask learning.
In the pre-training process, you considered prioritized sampling based off of how much loss there is?
Sorry, did we say again?
Do you consider prioritizing sampling in the pre-training portion?
So did we consider prioritizing the sampling? So in some ways with this pre-training strategy here, that's kind of what we did by basically focusing on these really hard tasks. And a lot of the gap in the end was improved by really waiting for 4 of the tasks at the very end, until after you're gone through sort of oversampling all of these really hard tasks. In the last 10 minutes, basically the most exciting thing for last, though, I think you could also do a lot more work in this direction. I mentioned this whole question pointer and zero-shot learning in the beginning, and we basically just tried to play around with that a little bit and found that in some cases it actually kind of magically works. So here we tried a sentence: John had a party, but no one came and he was all alone. And then we asked, is the story sad or happy? And while the model could have, generate some random German words or some random SQL words, or just said, whatever, it actually pointed to, of all the words it could have pointed to in the context or the question, it pointed to sad, which is pretty cool. And that's just one small sample, and you could do a lot more. You could try to come up with a very large zero-shot kind of classification data set, which is actually kind of hard too. You have to be quite creative. It's not like you can just say, oh, we'll just take all these reviews and label them as these, positive, negative. So I think we need to do more work in that direction. Somebody will hopefully create a zero-shot kind of task data set that is not just zero-shot for, kind of new distributions or something, but completely different outputs. But we tried a couple, and it doesn't always work, right? You can be adversarial about it. You can make, this basically looks most similar to, is the sentiment positive or negative? Is this sentence positive or negative? That was the formalism we had for sentiment analysis. And so you could, if you make the question more and more different, eventually it'll kind of get tripped up. And it's clear that it's benefited from the word vectors of sad being closer to negative, and then understanding sort of through all these correlations and deep representations that there are other sort of sad words in this context or whatever it is. And so it was able to point to this. But you can be adversarial. It doesn't always work, but even the fact that it was sort of zero-shot classification based on word vectors for new kinds of questions, personally, it was very exciting to me. And we tried a couple of other things, like Brian gave a talk and nobody clapped. Was Brian happy or sad? And it also got it right. So there are a couple of the examples where at least this happy or sad thing worked, and then a couple of other sort of adjective questions that we tried. But what I would be most excited about is eventually actually trying to have a zero-shot classification task that combines the different tasks too. So unfortunately, there's no data set for that, so we didn't train it, so it doesn't happen with the model. But in theory, if you ask what is the you can summarize, and you can translate from English into German, why couldn't you ask the model for a German summary? And if that worked eventually, that would be even more amazing. But it doesn't work right now because we never ask it sort of for these compositional task questions. But it's yet another interesting line of research that I think could spawn from this. All right, so I hope I could show you that this sort of decaNLP framework is an interesting new benchmark for generalized NLP. I do think it's a reasonably good framework for tackling a bunch of the really hard questions in the field, more general language understanding and question answering, of course, multitask learning, domain adaptation, which we sort of analyzed a little bit with the sentiment and SNLI versus multi-NLI, transfer learning, and then weight sharing. I think it's clear everybody loves weight sharing. You want to share as many weights as possible. Word vectors started it. Elmo, Cove, and now Bert basically share more and more, deeper and deeper layers. It would be great if we can unify that last bit also and then share basically the entirety of the networks, and then eventually hopefully get to zero-shot learning. Now there's a bunch of related work. The original paper has over 100 citations in it of papers to other lines of work, but these are at least some of the models and papers that influenced us the most in our thinking and modeling. One of them actually comes from the two instructors of the class. And so hopefully we can sort of think about what's next after all this architecture engineering. And I think one potential answer to that is single multitask learning for more generalized NLP models. All right, thank you.